This video is covering section 8.7, which is called L'Hopital's rule. We're actually going back to limits for this section, and I know in this unit we're talking about advanced integration, and limits is not in integration necessarily, but this is something that we have to learn in order to apply to our next section in 8.8, which is an advanced integration technique. So L'Hopital's rule, like I said, we're going back to limits. And it's a rule that we can apply to indeterminate forms of limits. So if we look here, the limit as x approaches 0 of e to the 2x minus 1 divided by x, typically when we were trying to solve limits, if the function did not exist at what I was approaching, then I would try some kind of algebraic manipulation, like multiplying by the conjugate, factoring, things like that, in order to get something that I could take the limit of. So initially, like I said, is if you plug in what you're approaching, so in this case 0, and you get a form that is dividing by 0 or something like that, then you would manipulate. So let's just see what this is when I evaluate first. So then I get obviously dividing by 0, and better yet, if I even evaluate that numerator out, you actually will get 0 divided by 0, which is called indeterminate. It is not 0, it is not 1, and it is not infinite. It is actually what we consider indeterminate form. Okay, so that means really we don't know what the answer is when we get 0 over 0. It could be any of those above things that I mentioned. Okay, so since this is an indeterminate form, previously we would try to rewrite that expression using various algebraic techniques. However, not all indeterminate forms can be evaluated with that manipulation, and this one is one of those examples. So we got 0 over 0, which is indeterminate. Also, infinity divided by infinity is an indeterminate form. And for the sake of L'Hopital's rule only applies if you have an indeterminate form of 0 over 0 or infinity over infinity. There are other indeterminate forms, which we'll talk about at the end, but these are the only ones that apply to L'Hopital. I also want to mention here where L'Hopital came from. L'Hopital is the last name of the French man or mathematician who came up with this rule. So don't say hospital or Le Hospital, it's L'Hopital. All right, so let's look at what we would do next. Before L'Hopital's rule, if we got an indeterminate form that we couldn't solve algebraically, then we'd go to the graphing calculator. So I've put this function into the graphing calculator, e to the 2x minus 1 over x, and you can see that as x approaches 0, the graph is approaching 2. So that's actually a limit there. So you see that when I evaluated this algebraically, we got an indeterminate form of 0 over 0, and then the actual limit is 2. All right, so what L'Hopital's rule allows us to do is find the limit of this without using a calculator. So L'Hopital said that if you have two separate functions, f and g, and those functions are differentiable, containing that c that they're approaching, if you're taking the limit of that function divided by another function, and you get a form of 0 over 0 or infinity over infinity, only if you get that form, then the limit of that quotient is equal to the limit of f prime divided by g prime. Now, do not confuse this with like quotient rule. We're not taking a derivative here. We're finding a limit. And so L'Hopital just discovered that if you get an indeterminate form, if you take the derivative of the top, divide by the derivative of the bottom, and then take the limit of that, then you will find the limit. All right, so let's see how this plays out. So obviously in part C, we have the same example. We already got an indeterminate form of 0 over 0. So what I like to do is I like to show what that limit would equal if I just plugged in the C, the 0 here, and see if I get a L'Hopital rule form, which again is 0 over 0 infinity over infinity. So then that's kind of like my side work, my scratch work. So I got 0 over 0, so what that means is, yes, I can now apply L'Hopital's rule, which for the sake of this video, I'm going to use LH for L'Hopital's rule. So I'm going to apply L'Hopital's rule, which says I can keep that limit, and I can just take the derivative of the numerator and divide by the derivative of the denominator. So that would give me 2e to the 2x minus 0 divided by 1. So now if I plug in 0 for x, then you get 2e to the 0, which is 2, which is what we found in the graphing calculator. So L'Hopital is actually one of my favorite things. I love L'Hopital's rule, but the rest of the examples, I know that's really easy to remember, but the rest of the examples is knowing when to use L'Hopital's rule, how to know what kind of form it is, and things like that. So example 2. Example 2 is actually one that you could have in the past factored and found the limit, but we're going to also show that L'Hopital's rule applies here. So as x approaches -1, if you evaluate the numerator, you would get 1 plus 1 is 2 minus 2, which is 0, over -1 plus 1 is 0. Okay, so that's kind of my scratch work there off to the side. So that means, yes, I can use L'Hopital's rule. Okay, so applying L'Hopital's rule, remember to keep the limit, and then that would be 2x minus 1 divided by 1, and now if I plug in -1, you get -2 minus 1, which is -3. Okay, example 3. So now where our limit is approaching -infinity. So you need to think about how these things are approaching as they approach -infinity. Now, when I'm doing L'Hopital's rule, I typically don't say like equals 0 over 0. That's not really something mathematically correct that we want to do. So I avoid the equals so that just in case an AP grader or something doesn't mistake that answer. So think of that as more like scratch work. So the limit as x approaches -infinity. If you plug in -infinity in for x and you square that, then that would be infinity squared, which is just another infinity, right? And then in the denominator, we have e to the -x. So if you say e to the negative of -infinity, that's e to the infinity, which is also infinity. So that is a L'Hopital form. So check, yes, we can move on. All right, so let's apply L'Hopital's rule. So this would be the limit as x approaches -infinity of 2x divided by -e to the -x. So then we see what we get. If we plug in -infinity, in the numerator we would get -infinity. In the denominator we would get e to the infinity again, which would be infinity, and then of course -infinity. So we get infinity over infinity again. Now, that doesn't mean we did anything wrong, and it doesn't mean that we can't find an answer. It just means that we have to apply L'Hopital's rule again. So sometimes you have to do L'Hopital's rule more than once. So then we get the limit as x approaches -infinity of 2 over positive e to the -x. And now hopefully you can see we're going to get a constant divided by my denominator is approaching infinity. And so also something that I kind of want to stay away from is writing 2 over infinity, because it's not really a thing, because it's 2 over something approaching infinity. And so as the denominator is getting really, really big and the numerator is staying constant, then this is approaching 0 is my limit for this problem. Okay, so example 4. The limit as x approaches infinity of e to the -x times the square root of x. Now, off the bat, you should know this is not going to be L'Hopital's rule, because L'Hopital is 0 divided by 0, or infinity divided by infinity. But if you went ahead and plugged in infinity, you would get e to the -infinity. And if you think of e to the -infinity, think of e to the x. Looks like this. And so e to the -infinity is actually approaching 0. And then you have that times the square root of infinity, which is infinity. And 0 times infinity is actually an indeterminate form. It's not 0, it's not infinity, it's indeterminate. But it's not of the form that we can use L'Hopital's rule. So what we need to do now is to rewrite this problem in a way that I can apply L'Hopital's rule. So we need to think of division. So this one's pretty easy to see. If I have e to the -x, then we can drop that down in the denominator and say that's e to the x. So now if I plugged in infinity, you would get infinity over infinity, which, yes, we could apply L'Hopital's rule. Okay, so for this first step, that was not L'Hopital's rule. This was just rewriting the problem. All right, now I can apply L'Hopital's rule that is in the form of infinity over infinity. So that will be the square root of x would be 1/2 x to the -1/2 over e to the x. And if I rewrite that, then you would get, and don't forget your limit, 1 over 2 square root of x times e to the x. Which now, if you plug in infinity, you would get 1 over 2 times infinity. So again, same as with example 3, you have a constant divided by the denominator approaching infinity. So my answer is 0. Okay, now for sake of time, I'm actually going to skip number 5. It's a really important problem, and we're going to actually talk about that one in class. But it kind of takes up a lot of time and a lot of space. So we're going to come back and do that in class. So I'm going to go ahead and skip to number 6. Okay, so as you can see, this is the limit as x approaches 2 from the right side, but L'Hopital's rule applies to one-sided limits as well. The reason why we have to have from the right side is because of the square root. All right. Actually, no, I take that back. That would be if we were approaching 1. So I don't know why we're approaching from the right side, but we're just going to apply the same rule. All right, so if I plug in 2 right now, you would get 1 over 0, right, minus 1 over 0. Now, we talked about if 1 is dividing by 0, a constant is dividing by something approaching 0, then that's actually infinity. So you get infinity minus infinity, which is actually not 0. That is another indeterminate form. Okay, so infinity minus infinity, you need to know that, is indeterminate, but not in the form that I can apply L'Hopital's rule. So I need to do something. I'm going to rewrite this in order to find L'Hopital's rule form. All right, so we're going to keep the limit as x approaches 2 from the right. And so now you can see that these are two fractions with common denominators, so we're going to go ahead and just put those together. So you get 1 minus the square root of x minus 1 divided by x squared minus 4. Now if you plug in 2, you would get 1 minus 1 in the numerator, so 0, and you'd get 0 in the denominator. So that is L'Hopital's form. All right, so now we're going to apply L'Hopital's rule. And so when we take the derivative of the numerator, that would be a negative 1/2 times x minus 1 to the negative 1/2 divided by 2x. If I rewrite that, then you would get negative 1 over 4 times the square root of x minus 1, and I forgot my limit as x approaches 2. And now if I plug in 2, you get negative 1 over, sorry, I thought I forgot something. That should be a 4x, my bad. So then when you plug in 2, you will get negative 1/8. And that is your limit for this problem. Okay, for my final problem that I'm going to do in the video, we have the limit as x approaches infinity of e to the x over x. So if I plug in infinity, e to the infinity is infinity over infinity. So check L'Hopital's rule works. So now we apply L'Hopital's rule, and we get e to the x over 1. So now if I plug in infinity, you get e to the infinity, which is infinity, which is the answer. This is an example of a limit that actually does not exist. It's just infinity. Okay, so sometimes that works out that way, and just don't be afraid of that. Okay, on this last page, there's not so many problems, just kind of some extra notes for you. So at the top, we have the all the indeterminate forms that you might encounter. So 0 over 0 and infinity over infinity, these are the only ones that you can apply L'Hopital's rule to. So the other ones, you have to figure out how to put those others into the form of 0 over 0 and infinity over infinity. Determinate forms that I want to point out, infinity plus infinity is infinity. Negative infinity minus infinity is negative infinity. 0 to the infinity is 0. And 0 to the negative infinity, I know this is really crazy, is infinity. If you want to figure out those reasons, then I'll let you look that up yourself. All right, so yeah, so again, remember that L'Hopital's rule can only be applied 0 over 0, infinity over infinity. Now, one other following application of L'Hopital's rule, and this is kind of piggybacking off of a little bit from the last example we did, but the last example we did, we had e to the x over x as x approached infinity. Now, if you look here, we have e to the x over x as x approaches 0. So if you had that, the limit as x approaches 0 of e to the x over x, and you plug in 0 here, then you would get 1 over something approaching 0. So L'Hopital's rule did not actually apply there. So this incorrect format, the person applied L'Hopital's rule getting 1, which is incorrect. So L'Hopital's rule does not apply for that one. That one is just simply equal to infinity. Okay? So that's L'Hopital's rule. I hope you enjoyed, and we're going to do that final example in class.